Hello everybody, welcome to activity 3.3. And what we're going to be doing today, you're going to be working independently within your teams to complete activity 3.3. And by the time you get to this video, you should be done with activity 3.3, and you're going to use this as the answer key to go through and to check your work. So the first thing we're going to do is we're going to go through the answers to A, B, C, and D. So what you were supposed to do is you were supposed to create a free body diagram for each of the four different phenomenon that you explored in activity 2.1 and we discussed in activity 2.4. So to help you out, I actually created the beginning of the free body diagram. All you have to do is apply, label and put the arrows in here and label the arrows for each of the forces that are being applied to each of these objects. So let's go ahead and get started with the answer key. So here is the free body diagram for the upper magnet. So this would have been for A. You were supposed to draw the floating magnet. So again, you're only drawing in the forces that are applied to the upper magnet. And it's the weight pulling it down and the lower magnet pushing it up. So how'd you do? If you were wrong with yours, change it so that it's correct. That way, if you have to, or again, remember, you can use these on the test. So that way you have the correct answer. So the next one was the magnetic cannon. You were only supposed to do the last ball, which was ball E. So we've got rail, or if you said a table, pushing up on it, you're correct, because we use the table and rulers. Sometimes we just use a rail. The weight pulling it down, ball D hitting it, and the magnet pulling it back. So you notice that ball D is the arrows larger, and that's because, remember, when you did this, ball E shot out. So if ball D's arrow and the magnets were the same length, ball E wouldn't move at all. But notice up here it says explain why the last ball begins moving. This explains that ball D applied a greater force than the magnet. Ball E shot out. So for the next one, we have the air-powered car. And it said think of the car and the fan as a single object. So that's why the car and the fan were together. So the table pushing up on the car, weight pulling it down. Again, there's no up and down movement. That's why these arrows are the same size. And there's only one horizontal movement that acts on the car and the fan. And this isn't the fan pushing out. The fan would have been pushing air the other way. It's the air pushing against the fan that caused the car to move. And then the last free body diagram that you were supposed to draw, this is probably the hardest one. And the reason why the flying balloon is so hard is because when we look at the balloon has air inside, and that air is pressing against the outside of the balloon in all directions. It's not only 360, it's three-dimensional. So it's really hard to draw that. So we did the best we could here. So treat the balloon and the straw as a single component. That's why we put it here. Explain why it starts moving. So we have the air outside the balloon. In fact, we could probably, if I was to draw this outright, I'd probably make this arrow just a little bit longer, because ultimately this is what causes it to move. So it's the air. If you think of the air flying out of the end of a balloon, that's not what causes it to move. It's applying a force in the opposite direction, but it's the air that's pushing back against it that causes the balloon to move. So I put that in here as a result of pushing back against the air leaving the room. So how did you do on the free body diagrams? Again, you're going to have to draw either a force model or free body diagram on the test. Now, eventually, we're going to have 3 tests in this book. You'll have to draw some of each. So be prepared to draw either one on this first test. So let's go through the questions. ES. What are the 2 forces that are applied to the upper magnet? Well, the 2 forces are the vertical pull non-contact force of the weight, which can be called gravity, or if you put earth, that's fine. And, actually, it's the magnet I have listed first. If you look at this, the 2 forces are vertical pull non-contact force of weight. That's actually of the Earth, so I have this typo here, and the vertical push non-contact repulsive force of the lower magnet. So this should actually say Earth right here because the magnet's applied down here. But notice how I talked about it's a vertical force, it's a pull, and it's a non-contact. So make sure you get in the habit whenever we talk about forces to put all three of those words together. And then which of these forces pull or push upward and which pull or push downward? Well, if you look at these, which of the forces pull or push upward? Well, it's got to be the lower magnet pushing up because weight's pulling it down. So the magnet's weight pulls it down because gravity always pulls objects down. So it's got to be the magnet pushing up on it. It's the only thing it can be. What should the relationship be between the two forces to cause the upper magnet to float? Well, they have to be equal. If the forces were not equal, these two, if they weren't equal, the upper magnet would keep going up, 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 up until it hit the top of the test tube. Or the weight would pull it down if the weight was greater until it hits the other magnet. So they have to be equal in order for it to float. When will the magnet start moving up or down? Well, it'll start moving down when the pull of weight is greater than the force of the lower magnet. And when will it start moving upward? Well, when the force of the lower magnet is greater than the weight. So we have to, right now the forces are balanced. We have to unbalance those forces to get movement to happen. So does the lower magnet float as well? No. And think about this. The lower magnet will never float because the magnetic repulsion that is subjected to acts downward in the same direction as the magnet's weight. So if you looked at the lower magnet is being pulled down by gravity and it's pushing against the upper magnet. So both of those forces apply a downward force on the lower magnet. So the lower magnet would be pulled down. If it wasn't for the test tube pushing up on it, the lower magnet would always be going down. It should never float. All right, so how are you doing so far? Hopefully you're getting all these questions right. So Jay, which horizontal forces act on the last ball? Well, we have the magnet pulling back on it. We've got ball D pushing on ball E. Remember, this is as it starts to move. We've got the weight pulling it down. We got the rail or the table pushing up. So the horizontal forces are going to be the magnet pulling it back and ball D. So which horizontal forces act on the last ball? So we've got the what? Non-contact pull force of the magnet on ball E, and then we've got the push contact force on ball E by ball D. And both of these are horizontal as it says in the question. So let's start taking a look at, the direction of the forces. How do we know what is the direction of these forces? Well, which way did the ball move? Well, we know the ball shot out to the right if we look at this the way it's set up. The magnet's pulling back on ball E, but ball D applied a greater force, and that's why the arrow is larger. And because it's larger, it would imply that ball E shoots off to the right. Now, the weight and the table, they're balanced. So there are vertical forces acting on ball E, but they're both equal. And because they're equal or balanced, there is no up or down motion. So there's only horizontal motion, and ball D pushes the ball off to the right. It's a greater force. What must be the relationship between these forces for the last ball to begin moving? Again, I already answered that. Ball D's got to be greater. The force applied by ball D must be greater than the magnet. Now, if you're starting to think, okay, Mr. Rattoon, I thought all forces are equal and opposite. Well, you're right, but remember, this is a free body diagram. So ball E is also pushing on ball D, and those forces would be equal. But when we look at the difference between the magnet and ball D, we're only looking at the forces applied to ball E, and because ball D applied a greater force, the ball shot out to the right. So how can, did I skip one? Yeah. Why do you think the car and the fan can be thought of as a single object? So if we remember the apparatus itself, I think I taped the fan to the car, and there was some putty below the fan, between the fan and the car, that stuck them together as well. So there's no benefits to having them be different. They're connected. And it's kind of like you in a car. We can think of the car and you as a system, and that's why we put the seatbelt on you, so that you are part of the car, and when the car stops, you stop. So because the car and the fan move together, nothing is gained by thinking of them separately. Which horizontal forces act on the car fan? Well, there's just one, the air. Now you might be thinking, what? The air? Is that the fan pushing the air out? No, no, no. The fan pushes the air out in the other direction. It doesn't apply a force to the car, but the air does apply a force. So it's actually the air pushing back against the fan that causes the fan car to move. And because it's the only horizontal force, it's what causes the movement. So how can the air apply a force to the car fan? Well, the car fan, when spinning, applies a force to the air. That is why the air gets blown by the car fan. So if you put the fan, it would blow air out. You could feel it on your face if you were to put the fan right up to your face. But now forces always come in pairs. So if that fan that's connected to the car is pushing in, outward, well, it's applying a force in that direction, but the car goes in the opposite direction. So think of the other pair, the air pushing back. And again, this is a free body diagram, so we're only looking at the forces that are applied to the car and the fan. And so it's this air, because that's the whole only horizontal force. This is the force that must cause the car and the fan to move. So in which direction does the air push the car fan? Well, in this direction up here, it would push it off to the left. It would push it in the opposite direction that the air is leaving the fan, because that air is being pushed against each other. Why can the balloon and the straw be thought of as a single object? Well, for the same reason we thought of the car and the fan together. They're taped together. There's no benefit to thinking of them as two separate pieces. Which horizontal force acts on the balloon straw? Well, if you look up here, the only force is the contact forces. Well, when we look at the horizontal forces, and again, this is one of those complicated ones. It's the air are the only horizontal forces. Now, some of that force would be vertical, because remember, the air inside the balloon is acting in all directions. And so the air pushing back would be in all directions. But we're not necessarily talking about atmospheric pressure. We're only going to talk about the air that's leaving the mouth of the balloon. So the only force is this air outside the balloon. So think of this as the air inside the balloon, and the air pressure is pushing back on it. So how can the air apply a force to the balloon straw? Well, the balloon straw, again, as the air is leaving the balloon, just similar to the fan, that's not the air that causes, or that's not the force per se that causes the balloon to move. It's the air pushing against that air, because remember, forces come in pairs. And we're only talking about the forces being applied to the balloon and the straw. So it's got to be the air pushing back that causes the balloon to move in that direction. So in which direction does the air push the balloon straw? Well, if we look at it here, it's got to be, and remember earlier on, I talked about maybe adding and making this arrow a little bit longer so it looks like it's longer. So the air is being pushed, the balloon is being pushed off to the left, because the air pushing against the air leaving the balloon is actually what causes the balloon to move. So, making sense questions. Under what conditions do forces counteract each other? Well, forces counteract each other when they are applied to the same object but act in opposite directions. When do they reinforce each other? When they act in the same direction. Now, if they counteract, doesn't necessarily mean they're balanced. It just means that they're being applied in opposite directions. In order to have balanced forces, or forces that cancel each other out, they have to be equally strong, and they have to act in opposite directions. So, how did you do? Did you get most of the questions correct? If you did, great job. You will be doing fine on the test that we're going to be having soon. So all you have to do is add these scientific principles, then you're done for the day. So 5, forces that are applied to an object in opposite directions counteract each other. And forces that are applied to an object in the same direction reinforce one another. So make sure you finish up any other things you have to for today. Make sure you ask questions if you have them. And remember, you'll do fine in the test. Make sure you've copied everything down you need to have copied down, because you can use your book on the test. You can use your notes on a test. And what I mean by notes is I'm really talking about this sheet here that you filled out. So as always, great job and take care.